Thank you again. Yes, so the talk today will be a totally different topic, and it's joint work with Avishai here, who's going to help you if you get stuck at some point, and then with my student also Jiapeng Zhang. And now there's this picture here on the top left corner, and at this point you should say nothing about it, and sort of hopefully by the end of, I'll say, the first half of the talk, which is going to be the first hour, hopefully you'll understand exactly what it means. So my plan is for the first hour just to use PowerPoint and give you a high-level idea of what's going on here, and then in the second hour, just sort of go to the board and give you proofs of the more technical parts. And again, if you have any questions, just stop me and ask. Okay, robust sensitivity. So what am I going to talk about? I'm going to sort of start by reminding you what is a sensitivity conjecture, which is sort of the motivation for this and some other recent works. And sort of, we don't know how to prove it, so we try to find some other more relaxed versions maybe we can prove. And sort of this is what we do here, and I'll show you some of the proofs, on the slides, and some more, on the board if you're interested. So what is a sensitivity conjecture? So it's really coming from trying to characterize properties of Boolean functions and how they relate to each other. And sort of what we know nowadays, after like maybe 20 or 30 years of work, that sort of, there are many, many properties that are in fact equivalent if you define equivalent as up to polynomial factors. So for example, if I give you a Boolean function and you ask what is its degree as a real polynomial, or you ask about if you want to approximate it in infinity by low-degree polynomials of the reals, or other combinatorial measures that if you know that you know, and if not, don't really matter for us. So all these measures are basically the same. So for example, if its approximate degree is some parameter d, then its real degree is some d to some absolute constant. And there's one property of Boolean function that is very natural that nobody knows how to relate to all these other properties. It is called sensitivity, and I'm going to define it soon. And sort of this conjecture says, well, we don't have any example separating it, so maybe it's the same. So it's the natural thing to conjecture. And again, we're stuck with this problem. Actually, I think I didn't silence my phone, just silence my phone. Okay, so what is this sensitivity conjecture? Maybe first let me define what is a sensitivity. So the main player in this talk is going to be a Boolean function. So you have a Boolean function from the n-dimensional cube to -1, 1. And -1, 1 don't really play a role here. They just think of them as the two coloring of the Boolean cube. But just this will be a convenient way of representing it. What is the sensitivity of a node? Well, different ways to define the same thing. So it's a number of neighbors in the Boolean cube of x, where the function assigns a different value than the one it assigns to x. Or equivalently, it's a number of edges in this Boolean cube that touch x, but somehow they cross the cut defined by this function. So every Boolean function defines a cut, all the edges that cross from a -1 to a 1, let's say. So all these edges in the cut that touch this node x. Or a third way of defining the same thing, just to make sure that we're all on the same page. So it's a number of directions, I in n, this is denoted as set 1 to n, such that if I take the value of f on the node x, and I compare to the value of the function on x, when I flip the ith bit, so this I use this to denote the flipping the ith bit of x, I get different values. Okay, so hopefully it's clear. So maybe another definition by picture. So if this is a Boolean function on a 3-dimensional cube, and unfortunately you can only draw 3-dimensional cubes here. So then we have some assignment to the nodes, red or blue. Then this node has sensitivity 3, since it has 3 neighbors of different colors. And this one has sensitivity 2, so it says 2 of different colors and 1 of the same color. Okay? Definition is clear? Some of you, many of you have seen it in the past, but some of you maybe haven't. So that's sensitivity. Now, what is a sensitivity conjecture? Basically, roughly, it says that if you give you a function of low sensitivity, meaning all nodes have low sensitivity, it must be a simple function. So I'll define this more formally in a second, but sort of, there are no interesting examples of low sensitivity functions to some extent. So this is basically this conjecture. And so what is max sensitivity is just sort of looking at all nodes and asking which one is a node that has the largest possible sensitivity. It has the largest possible number of neighbors of different value. And this conjecture, I think the first time to put this in this paper of Noam Nissan, is that if the maximal sensitivity is S, then all these other properties of Boolean functions, like for example, its degree as a real polynomial, but all these other notions are also polynomial in S. So they're not much bigger than that. Okay? So I'll give you another way of thinking about this in a second. It might be more natural.
I like to think of the max sensitivity as a notion of smoothness of the function. It doesn't change very much, and
Yes.
a polynomial is, a low-degree polynomial is another notion of smoothness.
Yes.
It
Yes.
makes sense in this informal setting.
That's true. Although I think here it's maybe from a combinatorial standpoint, it's more convenient to view this as a question about decision trees. But I'll discuss this second. I mean, but all these things are equivalent. I mean, just a bit of interpretation. So in terms of all that we know, all these bounds that we know are exponential in the sensitivity. So we know that there are some relations, but with these exponential gaps. So we believe maybe it's polynomial, but we can prove it's exponential. And sort of this original work of Simon, so this was like 4 to the s, and this is roughly e to the s, and this is roughly 2 to the s. That's just improvement in the constant in this big O. Okay. So here's another viewpoint on the same conjecture. So let's try to construct examples of, low sensitivity functions. So here's, the first example. Maybe the function just depends on the first s inputs, right? If the function just depends on the first s inputs, and I flip any other input, it doesn't change the value of the function. So the sensitivity is s. But you can take it one step further, says we can do it adaptively. So you can basically take what's called a decision tree of depth s. So you take this adaptive procedure where you query s points of the input, maybe adaptively. So you query the first coordinate, you get a 0, then you query the 17th coordinate, you get a 1, and so on. You do it s times, and then you decide on the value of the function. So this gives you a decision tree of depth s, and this also you can show that if you have any leaf there of depth s, and you change any value of the input that is not on this critical path from the root to the leaf, it doesn't change the value of the function. All right, so this is another example of a function of sensitivity s, and basically the sensitivity conjecture says this is it. You can't do anything smarter than that. Okay? So that's maybe a more combinatorial way of thinking about this, trying to come with examples for low sensitivity functions. So let me give you another equivalent definition that initially might not seem equivalent, but it's equivalent.
So the conjecture is exactly s?
No, it's a polynomial s. You might lose some polynomial.
What's the worst example that's known?
So it depends to which measure you're comparing it to, right?
Decision.
To decision tree.
It's with the new
S cubed.
S cubed? Okay. I didn't know that.
I'll work for it, yes.
I see. Okay, that's good to know. Okay, cubed. Yes, so you do get some non-trivial constructions, apparently. So what is this equivalent version? So this was sort of noticed by Gottsman and Lineal. So it's a question about subgraphs of the Boolean cube. So let A be a subset now of 0, 1 to the n. And for some weird reason, we'll require its size to not be exactly half the number of nodes. You'll see why in a second. And we look to define g of A to be the subgraph of the Boolean hypercube induced by A. So what does it mean? I take only the nodes of A, I remove all other nodes, and I just take the edges that remain between two nodes of A.
Two nodes
of A. Of A. So this is the sub.
The
Okay.
edges of the cube, yeah.
Yes. There's the edge of the cube that remain between two nodes of A. Okay. So here's a conjecture that turns out to be equivalent to the sensitivity conjecture. So either for A or for its complement, if you take this induced subgraph, it contains a node of high degree. High here is some polynomial in n, like n to the 0.1, some constant, right? N to some absolute constant. So this conjecture happens to be entirely equivalent to the sensitivity conjecture, although it seems different. Okay. And somehow notice that this is false if I allow the set A to have size exactly half, because, for example, if I take the set A to be all the nodes whose Hamming weight is even, then there are no nodes in G of A and in G of A complement.
There are no edges.
No, sorry, edges. Thank you. There are no edges. Right? Any edge must have changed the parity of the Hamming weight. And somehow this said that sort of this and sort of very similar examples are the only examples of that form. In particular, if you don't allow the number of nodes to be exactly half, you shouldn't have any examples, because all the nodes have low degree. Also, another interesting conjecture in this context is sort of, if A, let's say, is larger than half, then it makes sense that sort of the node of the high degree should be in the larger one of the two, either A or A complement. But we don't know if it's equivalent. It's a slightly strong conjecture, probably also true, but it's not entirely equivalent. So here's another viewpoint on the sensitivity conjecture from the lens of Fourier analysis. So let's take our Boolean. Now we're going back to our Boolean function, and now we decompose it to its Fourier coefficients, right? And now here's another equivalent version of the sensitivity conjecture. If the maximal sensitivity is some parameter s, then sort of you can compute f by a real polynomial of degree polynomial in s, which is equivalent to saying that I don't need all this full expansion. I can throw away all these Fourier coefficients where the size of t is large enough. And large enough here is polynomial in s, right? It's a degree of it as a real polynomial. So again, another way of viewing it is saying, take this function, decompose it to Fourier decomposition, you can just throw away all the Fourier coefficients where the Hamming weight of t is beyond some threshold, polynomial in the sensitivity. Okay, so again, these are all equivalent versions, totally equivalent versions. Okay, so now we don't have to prove them, so we want to somehow relax these notions. And there's been a couple of works in the last 2 years that sort of try to relax this in different directions. So the first result is, this is by Gopalan, Nissan, Sorvedio, Talwar, and Vigdorzon. And they said, well, maybe we don't know how to prove what we want to prove, but maybe there are other notions in which functions of low sensitivity are simple. And they show a variety of different ways in which they are simple. Just to give you an example for the results, if the max sensitivity is S, then, and you want to compute this function by a Boolean circuit, you don't need a very large circuit. You need only polynomial in n to the s. Okay, so other ways in which low sensitivity functions are simple. Okay? And the second work by, again, Gopalan, Sorvedio, Tal, and Vigdorzon, so 2 of them are here, is that sort of, we can go back to the original question about Fourier analysis and sort of relax the conditions of not saying the Fourier coefficients truncate at some point, but somehow they decay fast from some point. So this is really about the decay of the Fourier coefficients of such functions. And sort of this, what our work sort of builds upon that work, it sort of takes it, one step further. But I will really rely on a lot of ingredients that come out in this work, so I'll mention many of them. So again, so what do we want to prove here? So we assume f has bounded max sensitivity. So what is this sensitivity conjecture said? F can be computed by a low degree polynomial. And what this paper, Gopalan, Sorvedio, Tal, and Vigdorzon, but I'll just refer to it as GSTW from now on. What they proved is, in fact, well, we don't know how to prove this, but you can approximate this function very well in L2 by low degree polynomials. So you can compute exactly, but you can do a very good approximation. And I'll define this formally in a second. And this can be equivalently viewed as saying that the Fourier coefficients decay exponentially fast from a certain point onwards. So now let's define in a bit more detail. So we have a function with max sensitivity S, and it's a Boolean function, 2 minus 1, 1. So by Parseval, the sum of the Fourier coefficients is 1. So it's just a normalization factor. So what did they prove? They proved that, well, for any epsilon, you can approximate this function in L2 by a polynomial whose degree is not too big. What is not too big here is something like s times log 1 over epsilon. Okay? So if you go beyond level s, somehow you don't need, and if you decrease epsilon, you don't need a large degree. And equivalently, you can say that, well, we know what is the best L2 approximation. Just truncate the Fourier coefficient at a given Hamming weight, right? So its equivalent says, take all the sum of the squares of the Fourier coefficient. The sum of all of them is 1. But if you just start from Hamming weight s log 1 over epsilon onwards, it's at most epsilon. So equivalently, if I go to like lambda times s, it's at most e to the minus lambda. So it decays exponentially fast from level s onwards. Okay, so this is what they proved. If we assume that the max sensitivity is s, then from level s onwards, the Fourier coefficients decay exponentially fast. Okay? And sort of what we do in this work is saying, well, in a very high level, saying this is a very, this is a relaxed condition. This is an analytical condition. It's not really sensitive to being, exact. While this condition is very sensitive. You change one value of the function, it can change totally the maximum sensitivity. Just compare, the constant function 1 to the function that is 1 just in one point, that is 1 in all points except 1 point. One of them has sensitivity 0, the other one has sensitivity full. But somehow the Fourier coefficients are very insensitive to just changing one value of the function. So the question is, can we change this condition to a more relaxed condition that is insensitive to change a few of the entries of the function? Right? So somehow, if we get sort of a more, say, robust or relaxed consequence, it's nice if we start with a more relaxed assumption. And so let me show you how can we view this. Again, this was suggested in this GSTW paper. So this is, we can view this, as a distribution over the Fourier coefficients. I mean, this is a very common thing to do, because the sum of the Fourier coefficient squared is 1 for a Boolean function. So every Boolean function induces a distribution over sets T of numbers 1 through n, where we sample a set T with probability f hat T squared. Right? So we call this, so I call it this here the Fourier distribution of the function. Other papers give it a different name, but let me call it the Fourier distribution here. So what is distribution? So we sample this set T, but we output its size. We output the size of the set, so the Hamming weight of the set. Okay? So let's denote this as the Fourier distribution of the function. It outputs some integer between 0 and n, right? For any given function. And what we proved that if the maximal sensitivity is S, so this is equivalent of unit. So if I sample from this distribution, the probability to get a set whose Hamming weight is more than some constant S log 1 over epsilon is at most epsilon. Means again, it's equivalent way of viewing the result. So this distribution somehow decays very fast beyond level S. Now here's another potential distribution to look at. So this is also by this GSTW paper. Instead of looking at the maximal sensitivity, let's look at a typical sensitivity. Okay? Sensitivity of a typical point. So we're just going to sample a random point, x, and output its sensitivity, which is again an integer between 0 and n. So we have two distributions about integer 0 to n. The question is, are they related to each other? So they made this conjecture that sort of, if most nodes have low sensitivity, so maybe not all nodes, maybe there are a few nodes of high sensitivity, but somehow a typical node has low sensitivity, then the same result should hold. Somehow most Fourier coefficients should be supported on low Hamming weight coefficients. So and this is sort of a more relaxed assumption. If I change one node of the function, it doesn't change the typical behavior of the sensitivity. And somehow, another way of viewing it is that the sensitivity distribution controls the Fourier distribution. So what do we want to show? So we have a Boolean function, and we defined two distributions on integer 0 through n. The first one is this Fourier distribution, where we sample a set T with probability its Fourier coefficient squared, and we output the size of the set. Right? It somehow controls the Fourier decay. And the other one is about the typical sensitivity of a node. So one formal way of saying that these distributions, this control that is to say, for any constant d, the d moments of the first distributions are controlled by the d moments of the second distribution, right? Or formally, if I look on this is the expression that said what is a d moment of the Fourier distribution, and it cannot be too big by some constant depend only on d times the d moments of the sensitivity distribution. Okay, so this is one concrete way to formalize this notion of saying if the sensitivity is if most of them are small, then most Fourier coefficients should be small. So this is a convenient way to do it. And sort of equivalently, what you want to say is somehow the d moments, like I said, of this control the d moments of that, and what they proved is somehow the infinite moments of that, so the maximum sensitivity controls the d moments of that. And sort of this is what we show. So we show that somehow there is this constant, and it's actually not too bad, it's like d to the d roughly, that the d moments of sensitivity are an upper bound to the d moments of the Fourier distribution. Okay? So this is what I want to show you to you today. Okay, but first of all, are all the definitions here clear? Because there are lots of definitions. So are there any questions about the definitions? I mean, if you have questions, then ask now. No? Okay.
Yeah, nobody asked a single question. So.
Yeah, I don't know.
If D is 1, these are the same?
If D is 1, they are...
One
Yeah,
and two.
1 and 2 are the same, yes.
That was it.
Yes.
But you didn't mention, I don't know if you talked about it, there is a conjecture in the other direction also.
I'll discuss this also. Yeah, you can also ask other question. Is it true that, this is an upper bound on that? Somehow, if you know that the Fourier coefficient decay fast, does it guarantee that somehow the sensitivities are bounded as well? So we also partially answer that. So I'll discuss this also. But this is turns out this is sort of the more challenging part of the proof.
No.
What?
How come the one solved is more challenging than the direction that's not
I don't know. Because the other one is almost solved. No, the other one is almost solved, and the proof is much simpler. I'll tell you. But you'll see why. I know you're joking, yes. I know you're joking. And also, I want to mention that this GSTW paper gives an example where this AD cannot be super small, so it's at least something like d to the d times some lower terms, and we get something like d to the 12d. So our O is not some horrible quantum. So we get 12, and we didn't try to optimize it. I'm guessing if we try to optimize it, Avishai did some optimization. What do you get, like 4 or 5 or 2 even? Okay, even better. So yeah, up to some small constants, it's almost tight. Somehow getting here to be 1 is actually nice because this would actually give you nicer control about the Fourier tails, but let me sort of discuss this maybe a bit later. Okay. And so yeah, I'll discuss this later. So ignore this for now. So before I show you the proof, let me give you 2 related results. So the first one is going to be a direct corollary of that. And the second one is going to be sort of, the other direction, discussing the other direction. So it turns out it's the same way that Gotzman linearism and gave you this. Let me just go back a bit. You remember that we had this sort of graph. We had this graph theory equivalent version of the sensitivity conjecture. So you might ask, well, what if I know that this is not exactly half, but sort of is bound away from a half, the side of the set? Can you get something meaningful here? And the answer is yes. Where was I? Okay, good. So here's, the setup. So now let's say we have a subset of the Boolean cube, and its size is somehow, 1 plus epsilon times, half the cube. And again, we define g of a to be the subgraph of the hypercube induced by A. So here's a direct corollary of this theorem. I'll show you the proof in the second half, if you're interested. So either here or in its complement, there are many nodes that have high degree. Okay? So somehow, if you just do a simple averaging argument here, it's easy to see that there are nodes, a typical node would have degree epsilon times n. But actually, more is true. A large fraction of the nodes have a large fraction, a large degree, and somehow improving this d to the d, d to the 12, d to d to the d, would improve this polylog to a log. So this would be sort of one nice, still open problem, how to improve some constants here. But so far we get polylog, and again, this poly is not too bad. I mean, if you optimize, you get maybe log squared or something. Okay. Also, I want to mention that already the GSTW paper in this framework would say that there is at least one node whose degree is n over log 1 over epsilon. So without this poly, but only one node. And we can show there are many nodes. So again, I'll show you the proof of that, in the second half of the talk. Here's sort of talking about the reverse inequality. So what we proved, so this was the main result here, is that sort of there was this type of bounds. There's some constant, which is like d to the d. But can we also bound in the other direction? Are these two terms equivalent to each other or not? And so they ask, is it true that sort of we can also lower bound the Fourier distribution moments by sensitivity distribution moments? And we sort of have some partial answer to that. And I'm hoping we can be able to close the gaps here. So what we can prove is this is true, but not for all d, but for a large families of d's. So for every k, there is some d between k and k squared, such that the reverse direction holds. But again, this is just a thing, just because we're still working on this. I hope that next time I give a talk about this, we'll also figure this out by now. So I'll tell you about this also in the second half of the talk. And somehow, although it seems a very related question, the proof here is much, much simpler. So, yeah. Okay, so this is sort of the two side notes. So what I want to focus from now on is how to prove this main theorem. Okay. Again, any questions so far? Please ask questions, otherwise, yeah. I don't know what you're following. Okay, so again, just to remind you what I want to prove. I want to prove somehow, again, I slightly reformulate this main theorem. So instead of looking at t to the power d, I look at t choose d, but it's the same up to a factor of d to the d that we don't care about, and this will be slightly easier to work with. So again, I want to prove that this version of moments of the Fourier distribution is controlled by d moment of the sensitivity, and the proof is going to have 3 steps. The first step will be somehow to eliminate the Fourier moments from the equation together and replace them by a much more combinatorial object. And this is very similar to a step that was in this GSTW paper. And somehow the object that we need to study will be functions on D inputs that are sort of maximally complicated, that have maximal degree. And you'll see where they come up naturally. So then most of the work is going to be how to find various combinatorial property of maximally complicated Boolean functions. And then somehow we'll sort of tie it together at the end and to relate this back to sensitivity. But sort of most of the work is actually going to be on this sort of step 2 part. Okay, so we have these 3 steps. So first step is just eliminate the left-hand side by something more combinatorial.
It's probably, yeah, I mean, with all the work put into this, I think it's still hard to even give an intuitive idea why these 2 distributions should be related. That's a very strong
Yes.
relationship.
No, I fully agree. I fully agree. I don't think we. I don't.
It look like they're coming out of completely different
Yes. Yes. So.
information about the function.
Yes.
And yeah, the moments match perfectly.
Yes. So I don't have a good intuitive answer. I mean, I know that this has another way of thinking about this. It has nothing to do with Fourier. This is more combinatorial. You'll see it in a second. But again, I don't have any good intuition yet.
Yeah,
Still. Yeah. I agree. Really. Yeah. I think it was. Yeah.
Maybe I'll add one more thing. I think that the whole study is, the graphs of Boolean functions generated by these 2 colorings of the cube as a combinatorial object. I mean, which graphs arise this way, and which, what are the properties is a really interesting thing, and I think important for Boolean complexity.
Yes. That's one thing. That's true. But also another thing that you can sort of do once you have this sort of more analytical formulation is ask what if the function is not Boolean? What if sort of so you need to sort of slightly change the definition of sensitivity, and then there are interesting potential, conjectures that you can make. So we're still working on them. But once you move to this sort of more analytical setting, you can sort of say now a function from the Boolean cube to the reals. Can we relate these 2 things? Which sort of maybe you don't really need things to be Boolean. Okay, so step 1, sort of eliminating the Fourier moments and replacing them with something more combinatorial. So some definition. So a function from n bits to -1, 1. So what is a d-dimensional subcube? It's just a cube that you get by taking d inputs, saying they're free, and the rest are fixed. Right? It's just a d-dimensional subcube of the n-dimensional cube. And obviously if I take a Boolean function and I restrict it to a d-dimensional cube, it just gives me a Boolean function on d inputs. The d inputs I haven't fixed. Okay, it's clear. So then we'll study a lot restrictions of Boolean functions. Now we said that this restriction is has maximal degree, and think of maximal degree as sort of maximally complicated in some way. If its degree as a real function is d, so it's the maximum it could be as a function of the inputs, and this will play an important role. Okay, so this is the notion of a maximal degree restriction. It's a restriction where the restricted function has a maximal degree. So this is what we want to prove here. This is our main theorem, and the first step is just to simplify this left-hand side. So let me A be the left-hand side up to some scaling factor, and B be the following object. So I'm going to go over all possible d-dimensional cubes, and I'm going to count how many of them are maximal degree. How many cubes of d-dimensions are such that if I take the function and restrict it to this d-dimensional cube, I get a maximal degree function. And the claim is these 2 things are the same, up to some factors of 2 to the d. So instead of studying this object, you can just study this more combinatorial object. And it's the same thing. So again, we really don't care about 2 to the d factors here. They're really like low order terms. So I was and this was also sort of implicit in the previous paper. I'll give you some very high level idea why it's so I won't go into the proofs here. This is not really interesting, just some calculations. So what's a high level idea? So define some derivative operator of functions, basically mean take the function on x and flip the ith bit minus the function on x. So like a discrete derivative operator on the Boolean cube. And just apply it iteratively d times. So in d different directions, and compute the following expression. Take all the possible d derivatives of the function, square them, and sort of sum over all possible inputs, all possible directions. And the claim that this thing really controls both, what we had before, both before the Fourier moments and the d-dimensional cube. So why? So let me give some high-level idea why you should expect this to be true. What happens if I take the Fourier expansion of a function and I derive it in a direction? So it kills all Fourier coefficients that don't contain this specific variable, right? So maybe I'll write on the board. Right, so if I have a function that's the sum of f hat s minus 1 xs, and I derive it in direction I, so this just gives us, so some scaling 2, sum of f hat s minus 1 xs, but we only run over sets s that contain I. So if we do it for d directions, then we get only the sets containing these specific directions, and if we square it, then what do we get? We get f hat s squared, and how many times do I count the set s? Exactly the number of d tuples contained inside s, so it's s choose d. So this sort of naturally gives us this s choose, or I guess here it was t choose d factor. That's one way to think about it. The other way is saying, now let's take now if I'm applying d derivatives, and I must just as well fix the cube that only has these d directions, and if the function doesn't have a maximal degree, then it's going to be annihilated by doing d derivatives. So the only restrictions that survive after d derivatives are the ones that have maximal degree. Okay, so this is roughly the argument here, and there's nothing too interesting here, so let me sort of skip over the actual proof. So really what we can do from now on is just forget about the Fourier moments. So all that we want to show is that somehow, if we count all these maximal degree restrictions of dimension d, there are not too many of them, given some conditions on the sensitivity. And the way we're going to do it is sort of study them. So we're going to say, let's take a restriction that has maximal degree. So it's just a Boolean function of d inputs that has maximal degree, and try to identify Boolean, some combinatorial properties of it. And somehow at the end will relate them back to sensitivity. But for now, in the second part, I will sort of forget about sensitivity. So max degree restrictions. So it's a setup. We have some function on d bits that has maximal degree. Let me call this g. G comes from a restriction of my original function to a cube of dimension d. But I'll ignore this part now.
When you say max degree, that means that the largest Fourier coefficient is non-zero?
Yeah.
Yes, it's equivalent. Thank you. Yes, it's equivalent. So g hat of the maximal coefficient is non-zero. Thank you. Or equivalent, you write it as a real polynomial, you require full degree. All of the things are equivalent. And somehow we want to identify useful combinatorial properties of g. So again, we'll start by a lot of these combinatorial properties was identified in this GSTW paper, and then we'll extend them further. So the first definition discusses paths in the hypercube. So a path is just you start somewhere and you keep going in the hypercube. It doesn't have to be a simple path, you can do whatever you want. Okay? A path. And so we have these nodes v1, v2, v3 up to vm. And every edge goes in some direction, right? It's a hypercube, so every edge just flips one bit of the input. So we have m minus 1 edges here, each one some direction 1 through d. And first definition, we said this path is, let's say, sensitive for g. I think you called it proper, but let me call it sensitive for this talk. If whenever a direction I appears for the first time in this path, it must be a sensitive edge for the function g. Okay? Meaning, I take this edge, and I see, and this edge must flip values of g. Okay? So this shows sort of a picture of that, because it's a bit delicate notion. So here you have a function on 3 bits, and I define a path of length x, so v1, go to v2, to v3, to v4, to v5, to v6. I claim that this is a sensitive path. Well, let's see. The first edge is this one, and it's a sensitive edge. It has to be sensitive edge, right? The second one is in a new direction, right? So it has to be sensitive. The third edge is in the direction we've already seen before. So we don't care. It could be, the g could flip values, could not flip values, we really don't care, right? And then this edge is in a new direction, so it has to be sensitive for g, so it has to flip values. And then this last one is in the direction we've already seen, so we don't care what it does. Okay. So again, so this is a sensitive path. So let me just define some terms. So these edges where we flip values for the first time, so this one, and this one, I'm going to call sensitive edges of this path. The nodes where sensitive edges start are going to be sensitive nodes. And all the remaining edges are going to be non-sensitive edges. So non-sensitive doesn't mean that they don't flip values. It means that I don't care if they flip values or not. Okay, so here's some definitions. Any questions on this? So this was the first definition, and sort of first observation is that somehow if G came from a restriction of a Boolean function f on n bits, then this property of being sensitive for G is exactly the same as being sensitive for f. Right? Because G and f takes the same value on the subcube, and the path it contains at the subcube. So it's the same thing. Okay, just to remember. So here's the second property. This is a simpler one. The path spans all the directions, somehow, if I check all the possible directions I see in this path, and I get all directions. Or equivalently, if I take the minimal subcube containing this path, it's going to be the whole cube. It's not containing any face of the cube. Okay. And the second observation is somehow, if I tell you that, G the restriction of f, and I give you this path that spans all the directions in cube, and I ask you what is a minimal cube containing this path, it's going to be C again. It's not going to be a subcube of it, right? Somehow I can use this path to identify a cube. So the idea will be to use paths to identify max degree cubes somehow. That's going to be the idea at the end. Okay. So again, just to sort of show this by picture. So this path, V1 to V2 to V3 to V4 to V5 to V6 identifies this three-dimensional cube as a minimal cube containing it. So here's one of the central lemmas in this GSTW paper. Take any function on d bits that has maximal degree. You can always find the path in the cube that has three properties. One, it's sensitive for G. So this was our first definition. Where a direction appears first, it has to be in this path. It has to be sensitive for the function. It spans all the directions. And it's short. It has length linear in D. They actually prove some more properties, but let me ignore them for now. This will be enough for us. So it's short, and so it's sensitive, and it spans all directions. And the corollary, the direct corollary of that, is that we can directly bound the number of d-dimensional maximal degree restrictions, which is what we need to control the Fourier moments, by exactly what we need. So this is some scaling factors, this is some loss factor d to the d, and we get here what we really want to, what they got, the maximal sensitivity to the d. So let me show you this first, because we're going to build upon this idea, to relax maximum to some more average. And somehow I won't discuss it, but somehow you can refine this a bit further and improve this d to the d to 2 to the d. But I won't discuss this here. So how do we prove this corollary? So this I want to show you to you next. So again, we want to prove that the number of d-dimensional maximal degree restrictions is bounded by this quantity. And again, this is the main term that we care about. This is some loss, and this is just some scaling factor. So what's the idea? Let C be some d-dimensional cube where the function f has maximum degree. And let G be this restriction. So by this lemma, there is a path, that is sensitive for G, which is also sensitive for f. It spans all the d directions, and it has short lengths, linear in D. So I'm going to, instead of counting cubes, just going to count this path. And this path is uniquely identify the cubes. So just count this path. So how do we count them? We just construct them, step by step. So the first vertex could be start anywhere. So we have 2 to the n options, right, for the first vertex. Now, given a vertex, also out of these L nodes, we know that they're going to be D-sensitive nodes. These D nodes where the next edge is going to be the first edge in a new direction. So also let's enumerate those. Only L choose D. Now, what do we say? Well, if this node is a sensitive node, then this edge, the next edge, must be sensitive for f, right? And so there are not too many options for it, only the sensitivity of f at this specific node that we sort of upper bound by just the maximal sensitivity of all nodes. Now, if it's not sensitive, then this is some direction we've already seen in the past. We only saw d directions, at most d directions so far, so just choose one of those. So how many passes do we have in total? We just sort of combine this together. We have 2 to the n options for the first node. We have something like 2 to the order d option to which nodes are the sensitive nodes. And now once we fix this once, then for every sensitive node we have S max to the option, so totally S max to the d. And for all other nodes, we have d options, and the length is order of d, so we get what we wanted to get. So this was our main result. Okay, so this will be our starting point actually. So up until now, I just described basically the result modulo this sort of technical lemma, showing why these spaces exist. Any questions so far? I know there are tons of details here, so just ask me if you have anything that you're not following.
Probably you should mention that this is somehow similar or even inspired by the proofs of the random, the switching lemma for.
Yeah, I know that you say it, but sort of I don't understand this intuition.
Well, I mean, this is sort of analogous to Rasbow's version of the proof of the switching lemma.
I mean,
it's the same type of encoding.
Yes.
Only, sensitivity enters instead of
okay.
close size in the DNA. It's
Okay.
almost, it's so close. And it also leads to, this proof also leads to switching lemma for small sensitivity function, which is
Yes.
new.
Okay. So somehow, now let's ask ourselves, why did we actually need to use maximal sensitivity? Why can't we sort of go here and say, no, oh, this is just some typical node, we can use some typical sensitivity here. So what was the issue? The issue is basically that we don't really know how these things behave, So we don't know how, maybe the first node is random, but somehow if we go through this path, they might concentrate, and we don't have any way of controlling where we're going to get. So this is where things get stuck. This is why you need this bound of maximal sensitivity here, and not some typical sensitivity. Well, the first node is typical, very soon it could be very atypical. So instead of hoping to enforce it, let's just enforce this directly in the definition of what we will ask from our path. So let's just be very naive and ask the following condition. The first node, so which is vi1 here, so remember the first sensitive node is just the first node in the path. Just the first node, the one that we know is random, let's hope that this is going to have the maximal sensitivity out of all sensitive nodes in the path. Okay? So let's just hope, we just make a definition that is going to make our life easy. And let's hope that these things exist. So I want to require that the first node has a maximal sensitivity out of all sensitive nodes in the path. So now I'm sort of hoping for this sort of revised lemma that said, if you give me any maximal degree function, I can always, that is a restriction of a Boolean function, I can always find a path here that is sensitive for G, spans all directions, is short, same as before, but now also the first node has a maximal sensitivity. If we can prove that, then we can directly replace maximal sensitivity by typical sensitivity. Why? So let me just show you. It will be exactly the same proof, but now we're going to, instead of looking on maximal sensitivity, we're going to look on a typical sensitivity. So this is just the sum of the sum and not average as a normalization factor, but it's basically the typical sensitivity to the d power, typical d moments of the sensitivity. So let me show you why. And before we had this sort of 2 to the n times maximal sensitivity to d, which is obviously upper bound set. So that it's going to be exactly the same proof. So we start by the same way. Now we have this sort of more powerful lemma. So basically we're doing exactly the same thing. Just sort of flesh everything out. So the red path was the only path that changed. So we have this path that is sort of more powerful. So we enumerate the first node v1. v1 is like some point node x that is random in the cube. All the other sensitive nodes in this path have lower sensitivities than x. So we can just use x to bound all the sensitivities. We just get the sum of sensitivity to the d. Okay. So somehow if you can put this sort of more powerful lemma, then everything else comes for free. So the question is, why would we believe that this more powerful lemma is true? But everybody agree that somehow this more powerful lemma just gives us exactly what we want.
Or even the simple lemma is not.
Yeah, that is true. No, I agree. No, but given that the simple lemma, is true, like, why should we hope that the first node is maximal? No. So now let's try to do it. Let's try to prove somehow this sort of this revised lemma. So this is what we want to prove. So take any function d-dimensional that is a restriction of some larger function on n bits. We want a path p which is sensitive for g, spans all directions. First maximal here was just this name I gave for the first node having the maximal sensitivity out of all sensitive nodes in the path. And is short. But here's some annoying issues. Take the following, take the previous lemma without this. So this lemma is just defined in terms of g. I don't need to remember that g came from a restriction of a larger Boolean function, right? But now to discuss sensitivities, I need to talk both about the restriction function and about the overall function, right? You see, sensitivity is not a local property of g on the cube. It really is a global property of the Boolean function. So this is annoying. So let me try to remove this condition. Okay, so I want to remove somehow the dependency between the restriction and the overall Boolean function. So somehow I want to get like an F-free version of this lemma. So let me sort of, again, be naive and ask for something even stronger to be true. So take any maximal degree function and take any weight on the nodes of the d-dimensional cube. And this weight that we care about is really going to be some sensitivity of the Boolean function, but ignore that. Any weight. Take any path here with these sensitive nodes. Again, this is the first one. We say it's first maximal with respect to this weight function W if the weight of the first sensitive node control the weights of all the other sensitive nodes in the path, right? So now it's also decoupling, this path existence from being a restriction of a Boolean function. So I'm hoping that this should be true for any weight. Okay? And again, the whole goal of doing this is somehow just to study Boolean function on D inputs, not to study restrictions.
So the quantifier is that there exists a path which is good for all weights.
No. For any weight function, there is a path. But I'll show it in a second. Let me just sort of clarify the definition. And in fact, this was the picture that appeared as the first in the title slide. So now you have all the details of it. So now we have a path again here in the cube. And it's sensitive for this function G as before. But now for every node, I assign some arbitrary weight in some arbitrary way. Right, okay. And I claim this is also sensitive for this weight. Why? Let's see. First node here, that's the first sensitive node, has weight 17. This is sensitive, it's 4. This is not sensitive, so I don't care. This is sensitive, it's 13. This is 20, which is larger, but again, I don't care because it's not a sensitive node. Right, so again, this is 4, I don't care. This is not even in the path, I really don't care. Okay, so all of the nodes in this path, or also outside the path that have larger values, I don't care about them. I only care about the sensitive node in the path, right? So it's a bit of a delicate definition, but sort of it's what we need. And sort of, yeah, these are the sensitive nodes here, and among them, 17 is the largest one. So now I want to prove this is our main combinatorial lemma. Take any maximal degree function, any weight function. So given the weight function, there is a path, but it's not uniform for all. Obviously, given a path, I can always change the weight to make it sort of, yeah. So there is a path that gives what we want. So it's sensitive for this Boolean function G. It spans all the directions. It's first maximal for W, meaning the first node, if it has the largest W value, the largest weight among all sensitive nodes in this path, and it's short, linear in D. And this is like 2D maybe, if you can optimize these things. And this applies. We saw this. If you can prove this, then sort of we can prove our main theorem. So now all that we have to prove is why these things exist. So what I'm going to show you now in the slides is how to prove a weaker lemma, which replaces this length from D to D squared. This is much easier. And then I can show you the more details for how do you reduce D squared to D on the board. This is sort of more technical. So let me just show you how you prove it. This squared is not too hard. It fits in one slide, with a small enough font. So we're going to use induction on D. So we have a Boolean function on D bits and some arbitrary weight function. For every edge in the Boolean cube, let's define its weight. So just a maximal weight of the two endpoints. Okay? And let me choose a sensitive edge for this Boolean function G that has minimal weight. So I'm going to construct this path from the end to the beginning. Okay? This is going to be the last edge in the path. Okay? And let me just simplify my life. Let's use this edge. What it does, it flips the last bit, the diff bit. And also, so I can choose whichever one I want to be V, this one. Let's use that V has a D bit being 0, and obviously the other one has a D bit being 1. Okay? So this is our last edge in the path. So what do we do now? Now we say, well, if we have a function of degree D, maximal degree, and I choose any variable, and I restrict it to either being 0 or 1, for one of these restrictions, the degree has to stay maximal, D minus 1. If it's less than maximal in both restrictions, we can interpolate them and get a less than maximal degree for the whole Boolean function, right? So let's say it's maximal when I fix it to 0. This is why I chose this to be 0. Otherwise, if it's 1, I call this V and this V plus CD. So it has, maximal degree, namely D minus 1. So we now use induction. So by induction, there is some path here in this subcube, which is all these x's where the last bit is 0, which is sensitive for G and first maximal for W, right? And then we just have to take this path and I want to extend this to this node. So we have this path that ends somewhere, right? Oops, what happened here? It's not my computer, so I don't know.
Maybe you can go to the computer.
No, it's his computer. Okay, thanks. It's okay. Okay, so where were we? So the claim was that we take this path in the subcube C prime and extend it to this node V. Why can we do it? Well, once we've seen all the directions in C prime, we can use any edge with these directions. So we can go to any node that you want in C prime, right? Just using non-sensitive edges. We've already explored these directions. And this node V belongs to C prime. This is the way we defined it. So we just go to there and we just add this last edge and we're done. Okay, so this is a very, very simple inductive argument. Why do we get length D squared? Basically because, here we might need to go over D edges, right? So, yeah. So again, why D squared? So this extension path might use, I guess, D minus 1 edges, and you do D level, so you get D squared. Okay, so this is why you get D squared and not D. Okay. Somehow also this argument, also many of the arguments don't really rely on having maximal degree. It just relies on some complexity measure that is maximal, and if you take two restrictions by setting a variable to 0, 1, one of the restrictions has maximal complexity. So we don't have to use degree here. Okay. So again, my plan is to show you how to reduce the length of the path on the board later, but somehow it relates to sort of constructing a lot of combinatorial objects inside the Boolean cube. So we'll discuss all of this later. Let me just show you one of these objects because there's this nice conjecture from the paper that I want to highlight. It's a very nice natural conjecture. And if it's true, it will simplify all this combinatorial mess. So let me define. So from this GSTW paper, so what is a sensitive tree? So a sensitive tree for a Boolean function is a tree in the Boolean cube that has a few properties. Each edge of this tree is sensitive for the Boolean function. Okay, so each edge flips the value of the Boolean function. And also, each edge is in a different direction. Okay, so every edge has a direction, like whichever bit it flips, so every edge here is in a different direction. And somehow, such a tree automatically gives us a maximal sensitive path.
Before you say this, you probably should point out that just a vertex connected to its sensitive neighbors is a special case of a sensitive tree.
Thank you, yes. So this gives you a star, right? Take a node, connect all its sensitive neighbors, give you a star, right? But somehow this sort of tries to do more. And the observation here is that somehow if you could construct this sensitive tree for the Boolean function, then it automatically gives you this first maximal sensitive path for any weight function, because they take this tree, take the node that happened to get the maximal weight, and start a breadth first search on this tree from there. And this turns out to just give you a sensitive path, automatically. A DFS. Thank you. A DFS. So I wrote BFS, but I meant DFS. Thanks. So I just sort of do this path along this tree. Let's explore the tree. And somehow what they conjectured here is that somehow if a function is maximal degree, then there is always a sensitive path like that spans all the directions. So you can just use it. If this is true, you just use this tree and you can sort of construct this sort of what we needed here, this sort of first maximal sensitive path. But sort of we don't know how to prove this conjecture. The best they could prove is that there are these trees of size roughly root D and not D. So, and this is where things are currently stand. So this is sort of, this is open. So
all the edges have to be sensitive?
Yes.
Yes.
All the edges are sensitive, and you get every direction exactly once. So here are some related combinatorial conjectures. So let A be a subset of the Boolean cube of size strictly more than a half. And again, G of A is the induced subgraph. So sensitive conjecture, the star here, is that, I'll tell you what the star is in a second, that the maximal degree here is large, at least polynomial in N. Why is a star? Because it really should be here or in its complement. But if you're fair, it should be in the larger one of the two. So let's just call this sort of revised conjecture. I think this was actually asked in the paper by Fan Chang and Ron Graham some decades ago. Here's the conjecture for the last slide, equivalent version of it. There is a subtree here in G of A, or maybe it's in its complement if you want to remove the star, that the edges have unique direction and contain all the directions, right? So there is this maximal sensitive tree containing all directions, either in the induced graph on A or in the induced graph of its complement. And here's maybe an even weaker conjecture. Well, forget about the tree. either some connected component of this, or maybe its complement, that spans all the directions. And this is, in fact, it's true. It's a theorem. So I know that you proved it also, but I guess he proved it before. Yes, this is true. So there is this sort of, this is this paper on sort of bulky subgraphs, I guess, of the hypercube. It's a really cool paper. So yeah, so this weaker conjecture is a theorem, but it's not clear if this proof technique doesn't seem to give you a tree. It just gives some connected component, which is not enough for what we need here.
Maybe you should say that the size is exponentially and not.
It could potentially be exponential, I guess. I mean,
The size of the so
they get okay. Yes.
there is a big gap.
No, but now if you just want to a graph inside it or a path inside it, you don't have to take all the nodes, right? You just want to explore all directions, not all nodes. For this
If
stuff.
you take only sensitive edges.
Yes, that's true also.
you can do it,
That's true.
with the shop.
Yeah, I mean, I think this is what's known.
I mean, you didn't state it like this, but that's an example of a combinatorial question about graphs which connect only ones of a function to zeros of a function. What's the size of smallest connected component containing all directions?
Yes.
It just connects components, It's not even clear that there is one that contains all directions, and then you can ask.
Yes.
So very basic questions about connectivity, but just some graphs of Boolean functions.
No, I agree. Those are great questions.
So this size A greater than 2 to the n minus 1, does that guarantee that that this is a max, that the largest cohort?
Yeah, so for this one, yeah, so you just want to be more than a half for the theorem of Kotlov.
I know for the conjecture.
No, so the star here means here really that it should not really be this. It should be, either for this or its complement. But I mean, it's reasonable to suspect if it's true, it should be in the larger one. I mean, we don't have any, example showing where it's in the smaller one. But we don't. But formally, to be equivalent, you need to look. Because how do you get these things? I mean, it's very simple. You take a Boolean function and you XOR it with parity. So with the parity, just XOR in all the bits. So sensitive becomes insensitive and vice versa. So it just flips sensitivity to just being inside A or its complement. I mean, the direction is the relation is very direct here.
And the size being not 2 to the n minus 1 says is equivalent to the degree being n.
Yeah.
Yes.
So it means that the highest Fourier coefficient is non-zero.
Yes.
Oh, okay.
Yes. Thank you. Okay. So just conclusion before I move to the more technical proofs. What's a high-level message here? If most nodes in a Boolean function have low sensitivity, then most of its Fourier math is supported in coefficients with low Hamming weight. And sort of, because, so this is, let me just give you some questions before I discuss, the proofs. Can we use these analytical techniques to do something for the original sensitivity conjecture? So to me, it seems suspicious because somehow all that we do here, all these Fourier analysis methods, tell you about the uniform distribution, right? Or maybe about product distributions. Well, sensitivity conjecture seems to be about extremal points. So it seems to be a big gap there. Finding interesting application for the things, and improving the bounds and the reverse direction, all these more analytical question of getting the tight constants. Okay, so I think now may be a good point to switch to the board.
So you want to take
So-
we try mandated that there is always a break.
So what?
We take a break.
Sounds perfect. Yes. So how long of a break? Hopefully I have time for all three. So the first one, I want to show you how to use this main theorem for this approximate Gotsman lineal type of theorem. This will be a simple relation. Then I'll tell you maybe a little bit about what we understand about the reverse direction. And here, this is still. Here we still have work to do, so we understand some things, but not everything. And 3 is, this will be the more technical part, is somehow how do we reduce length? How do we reduce the path length? Path length from, order of d squared, which I showed you, to order of d. This will be the third point. Right? And again, if you have any questions, just ask. Okay, let's start with the first one. So the first one is really about translating two equivalent problems. So what do we have? What is the setup there? So we have a subset of the Boolean cube, and we assume its size is bounded away from a half. Let's say it's, maybe 1 plus epsilon times 2 to the n minus 1, 2 to the n minus 1. So it's bounded away from half the nodes. And we want to show that a typical node, so what we want is to show that many nodes in the induced graph on A or the induced graph on its complement have large degrees. And somehow this complement is just an annoying factor. I really want to show it here, but sort of the proof gives us here or there. And you'll see why in a second. So how do we relate degree to sensitivity? We just saw with parity. So let's define a function that's called maybe f1. It's just going to be the 0, 1 function on A, but that of rescale to be 1 minus 1. Because this is what we had here. So it's going to be minus 1 to the indicator. So f1 of x is going to be, let me write it like that. It's going to be maybe 1 or minus 1. It's 1 if x is in A. It's minus 1 if x is not in A. So again, just the indicator of the set A, but 1 minus 1 instead of 0, 1. And let's define the function f2 of x should just be f1 of x, XOR parity. So again, parity is just a function on n bit that sort of computer parity.
Plus minus 1 notation is just multiple.
Oh, thank you. You're right. Thank you. Yes. Times. Let's just write it as times, minus 1 to the x1 plus xn. So assuming my input is 0, 1 and the output is plus minus 1, so it's just multiply with parity in these spaces. And the whole point is basically, the sensitivity. So let's say if x is in A, then the degree of x in the induced graph on A just equals the sensitivity of maybe f2 on x, right? The number of nodes in f2 where it gets a different value are exactly the same as a node that sort of f1 gives the same value, right? Which is just a degree, right? So now we just sort of translate sort of degree. And similarly, if x is not in A, right, then just replace this with A complement. But if x is in A complement, it's the same thing, but it should be A complement, whichever one it belongs to. So now let's do this translation. Which board do I use? This board here. So now what was our theorem? Our theorem was that if I look on the sum, so this was I guess f2 of f2, just write like that. So the sum of f2 hat t to the d. So d is some parameter I will optimize in a bit, somehow depending on epsilon. This is controlled by something like d to the order d, the average sensitivity of f2 x to the d. Right? So this is just our theorem applied to this function f2. Now let's translate from f2 to f1. So what do we know? So this is just going to be d to the order d, the average of x, the degree. Just the degree of x. The degree means either in induced graph on A or an A complement, wherever x belongs. And what do we get here? Oh, I want to just logo bound this. So what do I know about A? It has measures bound away from a half. So I know that it's 0 for a coefficient. Its average is not 0, right? So I know that f1 hat 0 in absolute value is, I guess, 2 epsilon, right? Because it's not half-half. And since we saw with parity, then we know that f2 hat on the full Fourier coefficient here is also 2 epsilon. It's the same thing, right? So multiplying with parity just sort of swaps the sets. So we just lower bound this, but say this is lower bounded by, just look at the maximal t. So this is going to be this squared. This is going to be something like epsilon squared. That's going to be n to the d. So this is going to be epsilon squared n to the d. So this is, so we get the same thing here. The typical degree is epsilon squared n to the d, and then you just sort of you know, and we want to get sort of, now if you choose d appropriately, if you choose d to be something like log 1 over epsilon roughly, and you plug what you get, you see that the probability that the degree of x is larger than n over poly log 1 over epsilon is at least something like epsilon squared, or let's say epsilon to a constant. Okay, again, this is just sort of, I'm not going to do this calculation. I mean, typical degree is large. Okay, so this is one corollary, just sort of translating between degrees and sensitivities. Any questions about that? Okay, so this was the first thing. Second thing is the reverse direction, where we have some partial results. So now, item 2. So what do I want to prove? I want to prove that, you know, for the reverse direction, that if we look on the sum f hat t times squared t to the d, this should be greater or equal than some constant, let's say some constant here, times the average sensitivity fx to the d, right? So this is some constant, let's say ad. Right, so this is what we want to prove. Right. And we know that this expression is the same after the scaling of 2 to the n as counting d-dimensional cubes of maximal degree, right? So this is equivalent, so equivalently, so the number of maximum degree d-dimensional cubes, and now with this normalization, this becomes the sum, is larger than some constant times the sum over all x sensitivity fx to the d. Okay? And what we're going to do is we'll do something very simple. We're going to show that if a node has high sensitivity, it belongs to many, you know, maximal degree cubes. Okay. So this is the most, you know, direct way to do it. So let's sort of fix x and let s be the sensitivity of f on x. So what do you want to show? I want to show that the number of degree d-dimensional cubes should be roughly that, right? In fact, if you do the calculation, this in fact should be this choose d because of some annoying issues if the sensitivity is less than d or something, but you know, some small issues. So what do we do? So we say, what can we use? So one thing that we're going to use that we know this, there are these polynomial relations between different measures of combinatorial functions other than sensitivity. So in particular, we know that if the sensitivity is large, right, then the degree must be large as well. So the other direction we don't know. But we know that somehow, you know, if the sensitivity is s, it implies that the degree is at least some polynomial. It turns out to be root s. Okay? So we know something about the degree. It cannot be too small. So we want to apply it for this function exactly. We apply to restrictions of it. So let's fix some subset, some maybe k, which is, let's say, m, which is d squared. How do I say about it? So, okay. So we have a point, and it has s sensitive directions. And inside it, so just imagine you fix all the other directions. So we have an s-dimensional cube, and there's one point of maximal sensitivity. And you want to find inside it many d-dimensional faces containing this one point. Okay? So let's just sort of, you know, so fix some m-dimensional, m is going to be some parameter I'll optimize over later, cube containing s. Okay, there's some face of some larger dimension. So again, the sensitivity of x in it is m, because it's sensitive to all directions. Right? If I fix some directions, it senses to all the rest. So the degree here in this restriction is at least root m. Right? Okay. So I'm going to choose m to be d squared, so that this is going to be d. So the degree there is at least d. Okay? So now let's just, as a first step, let's just assume the degree is exactly d and see what happens. Then we'll see what can we do to the degree is at least d. So let's first assume this sort of, so assume.
What is the sensitivity of x with m?
It's what?
Why do you say that?
Because we have, it's fully sensitive. Right?
X is fully sensitive.
On its s directions. So all the other directions are fixed.
S is bigger. What is the m relative to s?
Oh, m is smaller than s.
Okay.
Thank you, yeah. M should be, where is it? So I'm assuming s is much larger than d, otherwise this coefficient is going to sort of kill you. So this coefficient at the end is going to be something like d to the minus whatever. So constant times d. So if s is like d to this, d cubed, it sort of kills it. But, okay, so we choose a small subset of the coordinates of size d squared, and let's assume, now for simplicity, that this restriction has degree exactly d. And then they claim we're done, because we found, what have we proved? We proved that inside any d squared coordinates, we can find a subset of them of size d that is maximal degree, right? So we're counting these d-dimensional cubes, and we might be overcounting a few of them, right? But not too badly. So what's a bit, so assume, for simplicity, for a second, that the degree in this restriction is exactly d. So how can we sort of lower bound the number of d-dimensional maximal degree cubes? Well, it's going to be at least, well, s choose d squared, right? So this is so for every d squared coordinates, this is the number of choices of d squared coordinates, there is at least one d-dimensional cube. But we overcount things, right? So how many ways are we overcounting a cube? But there's a number of ways of completing it to a d squared dimensional cube. So s minus d, choose d squared minus d, right? So that's a number, that's an upper bound on the number of ways that we're overcounting any specific d cube. And you do the calculation, this is roughly s to the d divided by d to the 2d. So I mean, so this is basically, that's the argument, that's it. So why can't we sort of get this exactly? Because I assume the degree is exactly d, but somehow the degree here is, I don't know, it's somehow between d and d squared. So now the question is, can we sort of, require to be smaller and smaller, and sort of, I mean, we're still working on it. So this is what we know so far. So somehow you see this is sort of much, much simpler. At least in hindsight. Okay, any questions about that? So the last thing I want to tell you about is sort of this main combinatorial work is how do we reduce the path length from d squared to d, which unfortunately is like this big combinatorial mess of a lot of combinatorial objects that come up. So let me show you that. So we need a lot of, we need some definitions for subgraphs of the cube. So just to remind you of the setup. Okay, I hope there's a way to get it.
Well, you have more, but these tools to read what.
Okay, yeah, I'll do it later, but there are tons of them here, so it's good. So again, let me remind you, so now point 3. So let me remind you of the question. So we have this Boolean function, g, from 0, 1 to the d to minus 1, 1. And we have some weight function from 0, 1, d to, let's say, the natural numbers, doesn't really matter. And what do we want? We want a path, p, in this cube, satisfies 4 properties. It is sensitive for g. It is first maximal for w. It sort of spans all directions, all d directions. And it's short, so its length should be order of d. Okay, so that's what we're trying to construct here. So let's see what do we need for that. Okay. Everybody remembers the definition for these things, or should I remind you of some definitions? If you don't ask, I don't know. Okay. So a few definitions. First definition that we've already seen is this notion of a sensitive tree. So I'm fixing this function g from now on, so I won't be saying sensitive with respect to g. Everything will be with respect to g. Okay, so I don't have to, so sensitive.
It's just a tree in the graph of g. I think if you had the definition of what the graph of g is.
Yeah, you can do that also. I agree.
Yeah. So
But this is confusing when there are in the path there are edges outside this graph, right?
yeah.
Yeah. So this is why.
I'm just pointing out that
Yes.
it's a very natural object. It's just a tree in the graph defined by the function.
Yes. Correct. So it's a subtree of the Boolean cube, 0, 1 to the d. So all edges are sensitive for g. Yes. And like we said, if you have a sensitive tree, it defines naturally a sensitive path, because you start wherever you want and you do a DFS on this tree. Just do this path on the tree, and then you end up where you started, and the length of this path is just sort of twice the number of edges. Right, so you go over every edge twice in two directions. And now we also need another definition, which is sort of shifting a tree. Also, maybe I'll sort of give some definition. So if t is a tree, so we need some definition. So v of t are going to be the vertices of the tree. I of t is going to be the directions of edges. So which directions this tree spans.
That's a subset of d.
Yes, this is going to be, so this is going to be a subset of 0, 1 to the d. That's a subset of d. And also c of t is going to be the minimal cube that contains t. Okay, so three definitions. So we said that a tree, take a tree t, and take some subset of coordinates, let's say I, that is disjoint from these directions. So we say that t can be shifted in direction I. Basically, if I flip all the coordinates in I, the value of the function doesn't change. So if g of x equals g of x plus, let's denote this by e I for all x in the vertices of the tree. So get some notation. So ei with capital I is a 0, 1 vector, indicator for the set I. This means flipping all the bits simultaneously in the set I. And when this happens, you can take this tree and you can shift it, and it's still going to be a sensitive tree, right? Because all the nodes have exactly the same value, right? And
So isomorphic copy.
yes,
The labels.
yes. And now, maybe I won't write this, but the point is, I will give another definition, which is a maximal sensitive tree. A maximal sensitive tree is a tree T that can be shifted in all I. All directions I that are disjoint from its directions. So why do they think the claim that these things always exist? This is already in this GSTW paper. So you take a tree. Let's say initially this tree is just take whatever tree you have. Let's say initially just an edge. Let's try to shift it in all directions. Disjoint from it. If I can do it, then it's maximal. If not, then at some point I get stuck. Right? There is some shift of it, and now I want to shift in this direction. I can't, because now the node here and the node here have opposite values, right? So they're not the same thing. So we can just add one more edge to the tree in a new direction and just continue this process. So if you start with any tree, you can shift it around and sort of grow new edges on it until eventually you're going to get a maximal sensitive tree. Okay, so this is like, no. So these things exist. So that's going to be the first combinatorial object. Okay, so they exist, but it's not clear when you get stuck. I mean, if this conjecture that we saw is true, then you might get stuck and get all the directions, but then you get stuck before that. So what they showed that you get stuck at root D, but we won't need that. So
you get what is called an orchard of trees.
Yes. Yes, but so I don't want to define this here. So I want to sort of,
just like to imagine you have a lot of these trees.
yes, and you have all these trees and they're all parallel to each other and they're all equivalent to each other. Because that's going to be the first definition of sensitive trees. But since we don't know how to get them to be full dimension, we need to sort of compose them together. So the second definition is, I'll call it a tree chain, which is sort of implicit in this in GSTW. So you're just composing trees together. So what is a tree chain? So it's a sequence of trees, so T1 up to Tm. So they're all sensitive trees. So I'll just write tree. So whenever I write tree, I will always mean sensitive tree. So I don't want to write sensitive again and again. It's a sequence of trees that satisfy the following property, such that if I take the vertices of Ti and I intersect it with the cube of Ti minus 1, it's not empty. Okay? And the claim is that if you have now a sequence of trees of that form a chain, you can start wherever you want on T1, and you can define a sensitive path that goes to T1, T2, T3, T4 up to Tm. Why? You start at T1 wherever you want. You explore all the directions of this tree using a DFS. And now you can go to any point in this cube because you've already explored these directions. So you go to a point where there's a vertex of T2. And then you explore T2, right? And then after you explore T2, you can move to any point in this cube, and sort of, you go to T3 and so on. So these allows to define this path, right? So they sort of define this. So they define also a path. So what we wanted to be, we call this a sensitive path. Okay? And one property that would be nice here is that you can actually get them to be disjoint. So we say they're disjoint, so it's a disjoint chain if each tree goes in different directions. If I T1 up to I Tm are pairwise disjoint. Pairwise disjoint. Okay, so now we never use the same direction more than once, and so this path is going to be short. And what GSTW showed that these things exist. So, and the way the proof goes is roughly, so you start with a maximal sensitive tree, and then you say there is some restriction for these directions where the function still has a maximal degree. You do build recursively, so you shift it to hit this path. So I'm not going to show you this proof, so we just assume these things exist. And the question is, why is this useful? Well, it's useful because if you only have maximal sensitivity bounds, then you say and let's say you span all the directions, then it gives you automatically this path that's sensitive. You start at T1 wherever you want, and you go to T2, to T3, to T4, to T5, until to the very end. But somehow it's not very useful when we have this second condition of being maximal for W, because if the maximal node for W, let's take the maximal node of the maximal value that W gets on any vertex of these trees in the union of all the vertices. If it happened to be in T1, then we're lucky. We start there and we go all the way. But what if it's at T2, right? Then I can explore T2, T3, T4, but I can't go back to T1, because this is a one-directional chain, right? It doesn't.
If it was a cycle, you would be fine.
If it was a cycle, it would be fine, but it's not a cycle, so we'll try to make it a cycle, right? Or at least reversible. So the next definition will be try to allow us to go in the other direction, but somehow to do that, we need sort of slightly weaker object. So maybe now I'll use the board here. So now to go in the other direction, we will need, unfortunately, something we call it a weak chain. So what is a weak chain? It's a chain that has sort of, weaker properties. So we have, again, trees. T1 up to Tm are trees. But now we require such that the vertices of Ti should intersect the cube of all the previous trees, T1 up to Ti minus 1. Okay? So somehow we can't only use the previous one, we have to use sort of, all of the previous directions. And this will somehow, because this is what we get. I mean, we don't want to get this, but this is what we get. So now I'll define a way of combining trees and...
It's easier. Any chain is a weak
Yeah, any chain is a weak chain, but not the other way around. But also weak chains might give you longer paths, right? So if you have, a tree chain and it's disjoint, it's automatically give you a path of length 2D, right? Because every direction you want to explore, or maybe 3D, explore 3 times. But this might give you D squared, because you might be re-exploring directions in T1 many, many times, right? So it's not a priori clear that it is useful to go from D squared to D. Okay. So the next object I'll define is going to be a reversible chain. And let's just use it. So a reversible chain is basically going to be 2 things. It's going to be a regular chain, T1 up to Tm, like this notion of a tree chain. We're also going to have a weak chain in the other direction. So starting from T prime M, going all the way to T prime 1, right, somehow. And this is sort of contain that. So it satisfies 2 properties, such that, so one property is that Ti is a subset of Ti prime as a subtree, right? So it's a subtree inside Ti prime. And the second property is if I take the directions of Ti prime and I remove from it the directions of Ti, they are pairwise disjoint. Okay, so somehow this weak chain might reuse directions, but not too often, right? At least only twice somehow. Okay, so this is an object. So we know that we know these tree chains exist, and we know these weak chains exist because somehow they're weaker. But somehow now I want to combine them together. So before showing you how to do that, let me show you why it's useful. And roughly it's going to be useful because it allows you to go up and down during this tree chain, right? So you can start wherever you want. So now let's try to use this. Okay. So I want to show you 2 things. First is why it's useful, and the second is how to construct them. Yeah, and by the way, when I wrote there this cube with multiple trees, I just mean the minimal cube containing all the trees. So I haven't said that. So it's not the union of the cubes, it's the cube containing all of them. It's a larger cube. So I want to show you why it's useful. So I want to show you that somehow, if we have this reversible chain, that sort of, that spans all directions, this sort of implies what we want, imply the path that we want, right? So why? So we'll just construct it by hand. So let's consider the nodes of, take the union of all the vertices of Ti prime. So all these larger trees here, and take the node here V, such that the weight of V under our arbitrary weight function is maximal. So we're going to start the path there, right? And obviously, if we start a path at them, and the path is just going to be, all the sensitive nodes are going to be contained inside this union, so it's going to be maximal first, by definition. So what do we start? So step 1, we're going to just run a DFS on Ti prime, that we can do, right? Because it's a tree. And then second step is that we go to some, let's say, Vi in Ti. Ti is a subtree of Ti prime. So after we've explored it, we just move to another node in this tree, right? And then because it's in Ti, and since Ti up to Tm is a regular chain, we can move in one direction. So we use this path in this tree, Ti up to Tm. So we can go through Ti, Ti plus 1, Ti plus 2, Ti plus 3, and so on, up to the very end. And then you can move in the other direction. y. And step 4, we move a path in Tm prime up to T1 prime. Right? This chain allows us to move in the opposite direction, but somehow it might be costly. We can show it's not costly, but at least we can move in this direction because we start with Tm prime, and then we can move to the next one because its cube contains the vertices of this, and to move to the next one, we might move to this larger cube of Tm and Tm minus 1, and then move to Tm minus 2 prime, and so on. So we still have this chain, but we might need to change more and more the variables as we go along. So it gives us a path, but it's not clear it's a short path. I want to prove to you it's a short path. It's not a priori clear. Okay? And somehow this property, the second property, is going to be important for that.
When you say go back to T1 prime,
Yes. Right? In this chain, I can move from Tm prime to T1 prime.
yeah, you can. I mean, just if the largest weight is in Tm, I mean, maybe we just might as well look at the largest weight is in Tm. You only go back.
Yes.
That's all.
Yes. I go back. But if it's somewhere in the middle, I have to first go up and then go down. I can't start and then go down. So this chain allows me to go up, but yeah. But the weak chain requires me to start here I can start wherever I want in the regular chain and go up. In this weak chain, I have to start at the beginning. I can't start wherever I want. Okay. So now I want to show you why this path is short.
But when you go back, you have to explore in the previous, let's say you start at Tm.
Mm-hmm.
For each Ti, you will do a depth first search.
Yes.
You didn't write it. I mean, since
Yes.
depth first search only in Ti.
Oh, here? Yeah, so this is what I explained before for the chain. So how do we do it? We do this DFS in Tm.
When you go back,
When you go back, yeah, I do the DFS in Tm prime.
you didn't say it.
Well, it's not exactly what we'll do, but you can. If you do it like that, you might lose too much.
So you didn't say what you did.
No, I didn't say exactly what I did.
That's not
Yes. I didn't fully specify what I'm doing. If you do it naively, you lose too much. So you have to be a bit careful in how you do it. But let me just argue that these 3 steps are very cheap, right? Because this is the only step where we might sort of lose a lot, more than linear in D. Right here, obviously, we're going to lose, the number of nodes. So what's the length here, right? So the question is, what's the length of the path? So here, it's like the size of the indices of Ti prime times maybe 2. So it's like, less than 2D. And here it's at most D. And here it's also at most D. So here's the only place where we might lose something that's not linear in D. Right? Because we might reuse Tm prime for many follow-up cubes. So then with this part we do a bit carefully. So how are we going to do it? So we're going to sort of, let me try if I remember. So we want to pick. So we want to choose like maybe Vm in Tm, and we want for this to somehow move to Vm minus 1 in Tm minus 1, and somehow to Vm minus 2 in Tm minus 2. Sorry, I think this is the right thing I want to do or not. So I have it here, so just to make sure I'm not making mistakes. It's a bit subtle. So this should be in prime. Right, so this is, so somehow we pick some node, in these trees, and we go from here to here to here. And let's see how many steps are we doing. So what are we doing? 1 second. I looked at this before the talk, but it always confuses me a bit. Okay, so first let's see. So what are we doing? So how can we do this path? So what do we do? So basically, so let's do it like that. So I want to run a DFS in T prime M, right? And sort of finish at V M. Right, 1 second. Okay, so what are we going to do? We're going to run DFS in VM prime that sort of finishes at VM. Okay, and then we're going to go from VM. We're going to go from VM to VM minus 1 using some shortest path that we need to compute.
So you want VM minus 1 to be in the cube.
To be in a vertex of this. Yes.
You wanted this weak chain.
Yes. So it has to be here, intersected the cube of T prime M, right? So that we can move to it using only directions we've already seen in T prime M.
It's possible you will get to another, I mean, a weak chain will lead you to some.
No, so I'm saying, so we have this weak chain. So by definition, there is some node here that is in the vertex of this node in the cube of the previous one, right? And here, for example, this will be also inside the cube defined by Tm prime and Tm minus 1 prime, and so on. Okay? Yeah. So it's all the previous ones. But I just choose one node arbitrarily to fix. So we go from Vm to Vm minus 1. We can do it. So we need to somehow bound how long this path is. We'll do it in a second. And then sort of we run this DFS in T prime A minus 1. That sort of also finishes at V M minus 1. So we start and end at the same node. And then we go from Vm minus 1 to Vm minus 2 using some shortest path. And so on. Okay? So that's the way we construct the path. Okay. So now let's bound the length of the path. So first let's look at the DFS. Okay, the DFS part, so what's the length of the DFS path? So it has two parts. There's the DFS part and there's the part of connecting trees, right? First notice this is in fact a sensitive tree because, for example, here we go from Vm minus 1 to Vm minus 2, and this belongs to the cube that already was defined. Right? So maybe this shortest path is long. We haven't proven that yet. But we're going to show it's short, but it's still at least legal. So what's the length here? So what's the length of the DFS part? Well, let's see. So it's going to be the sum of all the sizes of directions of Ti prime. Right? But actually, this is not too long. Why is it not too long? Because we know that all these directions, if I remove the directions of Ti, they're disjoint. Right? So this is at most, or maybe up to some constant, like 2 or 3, d plus the sum of the lengths of Ti, but these are disjoint. So this is 2d. And this is just the number of directions that we explore, and you go through every one twice, and then this, so it's like maybe it's like twice that, and here this will be 2, and this will give you 4. Anyways, up to some constants. Okay, so this part is fine. So why is this shortest path short? So let's look, for example, on this shortest. So how can we bound the length of the shortest path from Vi to Vi minus 1? So what we're going to do is we're going to use the regular chain to bound the lengths in the weak chain. So we're going to use this property now. So let's so one way to get a path is we're going to choose Vi prime in Ti. Now remember, this shortest path doesn't have to be sensitive. It's just any path, right? So we can forget about sensitivity. And we choose some Vi minus 1 prime in Ti minus 1. And instead of going here, we're going to go like that, right? And now this is, I'm sure this is a short path. Why? What do we go here? These directions here only use,
So you go in the other direction.
what it?
Start with Vi minus 1.
I think if we go from Vm to Vm minus 1 and so on, right? Anyway, it's a direct.
You are going on the forward chain.
Yes, but I wanted the end to go from Vi to Vi minus 1 in this reverse chain, but this is an undirected path, right? And we don't care if it's sensitive or not. So yeah, I agree. We might as well move in this direction, which might be easier to analyze. You're right. So let's just move in this direction, because we just care about this as an undirected path in this graph. So what do we do? So we start from Vi minus 1, that's in Ti minus 1 prime, and this is in Ti prime. So we just care about the distances between them on the graph. So what's the distance between these two things? Well, the distance here is at most, the Hamming distance is at most the number of I Ti prime. Why? Because Ti minus 1, or minus 1. Ti minus 1 is a subtree of Ti minus 1 prime, right? So we just need to use edges in this tree. And similarly here, it's at most I of Ti. And here, because it's, because it's a regular chain, then we know that we can just use things in this cube to move to this node here. So in fact here, so we just move to a node here that intersects this. So this is in fact going to be at most I ti minus 1 plus I ti. So everything here is bounded if you go sort of, in this not direct path. So and this, if you sum all of them together, you get something in R&D. Because it's a bit subtle, but sort of, sort of the nice thing here is that you need to use this direct chain to control the walk in the opposite direction. Make sure it's not too long. So, okay. Any questions about this part? So the last thing I have to show you is sort of, why do the things exist? And somehow, I'm not sure if I'll have time to show the full details, but it's sort of this dynamic process that creates them. So maybe I'll show you some ideas. It's not hard, just it's sort of a bit subtle. So now I want to show you how to construct. So I want to construct these reversible tree chains. Reversible chains. So the starting point will be that we know that we have this forward chain, right, from GSTW. So we're going to use this to create a backward chain. So what we start from, so starting point is going to be, we have T1 up to Tm here. And we're actually going to change it throughout. So we're going to apply various changes to this sensitive to this tree chain, and along the way also creates a backward tree chain. So we want to so we'll satisfy the following invariants. So we construct Tm prime up to T1 prime in this order. And when we do that, we also shift. We will also shift T1 up to Tm. So it won't stay the same chain that we started from. It will shift along the way. So let's start with doing Tm prime. So we're going to have this following invariance. So let's say so at some point we're going to construct Tm prime up to Ti prime for some I between m and 1. So after we shift things around, so this is always going to stay a sensitive chain. Let me not write this. So Ti is always going to be a subset of Ti prime. Yeah. So that's going to be a weak chain. Yeah. So I won't write it, but T1 up to Tm is going to stay a regular chain. That's going to be a subset of that. And the cube defined by Ti up to Tm is going to be the same as the cube defined by Ti prime up to Tm prime. And I think that's all that we need. Yeah, I think that's all that we need. Okay? So this is with the invariant. So once we go to I equal to 1, then we got exactly one. This is a weak chain, the regular is the chain, it's contained, and it's a full cube. So once we get I to I equal 1, we're done.
But for m, doesn't it mean that Tm equals Tm prime?
So that's where we start. But we're going to change things. So this will change along the way. So when we construct them, we also have to change them.
The invariance does not imply directly that Tm.
Oh, okay. So I don't claim, this doesn't hold for all I simultaneously. So we're going to construct this for m, and then we're going to change them and construct for m minus 1, and then change them again. So if one they hold for I, one this holds for I, it doesn't have to still hold for I plus 1.
I does not.
No, it does not hold for I plus 1. Things are going to change.
Yeah. But you have to maintain this disjoint parallel to disjoint.
Yeah, this will sort of follow, automatically at the end. Yeah, but you're right. But let's just also do this here. And also I ti prime minus I ti are going to be disjoint, pairwise disjoint.
And when you're saying variant, it means it always holds, but it doesn't. It just changes for every I.
So here, sorry. So this, sorry, I guess I didn't say anything right. So this should be for, yes, let me write this more formally. This should be J for all J, I through M. So all the ones we constructed so far. Yes, thank you. Okay, so we just do it sort of, greedily, one by one, but everything has to change along the way. Okay. Don't need this anymore. So the way we start is very easy. So if for I equal to M, we just choose T prime M to be Tm, and we're done. And so just you can verify this satisfies the conditions for I equal to M. That's the base case. So now let's say that. So say So let's assume we did it for I plus 1, and then we want to do it for I. Okay. So what do we do? So first of all, we want to sort of extend trees in the directions of ITI. So intuitively, I want somehow to extend Ti plus 1 prime up to T m prime in directions in I Ti. So now I want to add these new directions from ITI. So what do I mean by that? I mean, we're doing exactly the same process of getting a maximal tree, except here I don't allow to shift in any direction, only in directions that are sort of, subsets of the directions of the Ti tree. So what are we going to get? So what are we going to do? We take all these trees together, and we ask as a collection, say, is it true that if we shift all of them in all the directions here, the function doesn't change? So the value of the vertices don't change. If true, we're done. Otherwise, there's some shift or we get stuck. So one of these vertices, in one of these new directions, I can't shift it. So there's a sensitive edge. So we take this sensitive edge and we add it to one of them. Right? Just one of them. And then we keep doing that. So what are we going to get at the end? So we're going to get, so what do we get? We get new trees. So we shift those around. So let me not write it, but they get shifted around in directions here. So we shift each Tj prime. So here J is from I plus 1 up to M together, so simultaneously. Simultaneously in some direction. Let's say J prime inside I T I. And we extend them, right? So we extend. So Tj prime now is be a subset of T double prime J. And all of these things, and I know that I of T prime J minus I Tj, these are all disjoint, right? Because whenever I saw a sensitive edge, I just add it to one of these trees. So they're all disjoint. And they're all sort of in all subsets of I, Ti. They're all directions of this tree Ti that we're trying to add. So we did this greedy process, and we got now maybe a larger trees contained in some simultaneously shift of these previous trees. And now we shifted this by some direction. So we're also going to shift. So we want to maintain this property that Ti is a subset of Ti prime for all J here. So we're also going to shift each Tj, again, J from I plus 1 up to M by this is the same direction, by direction Ej prime. Same direction. So this maintains the property. So we shifted Tj and Tj prime by the same shift, so they still contain each other. And I want you to know that T1 up to Tm is still a chain. Why is it still a chain? Well, these are still sensitive trees because when we shift them, they have to stay sensitive trees. And we only shifted in directions in Ti, so it's still connected to the cube. So Ti plus 1 is still connected to the cube defined by Ti. So it's still a chain. So this will be the first operation that we do. And also, now these new trees are invariant. So let me also define, okay, space here. So let me also define maybe, I prime to be these directions of the tree Ti that we haven't, that we're invariant. So this is minus the union of the directions of Tj prime. So j going from I plus 1 up to m. So my claim is that sort of, all these Tj primes are invariant to shifts in directions inside I prime, right? So they're still invariant. Since we haven't grown new edges in these directions, they must all be invariant to all these shifts. So we need to use it as well. So this was the first step. Okay. Let me think for a second. Maybe look at the paper, it will be easier. Okay, now all that I'm going to do is I'm going to sort of set, now I'm going to set Ti prime to be Ti. Okay, so now I'm going to add this new tree to the backward chain just to be Ti. And I claim that now this satisfies all the properties that we needed. So let's sort of see why.
I guess the only thing you need to worry about is the weak change.
Yeah, but let's just verify the easier one first, right? So this is true because we said we just shifted this, some suffix, by something that maintained that all of them stayed sensitive and it was in the direction defined by Ti. This is true because we shifted both of them in the same direction, and then maybe we increased this. This remained pairwise disjoint because every new direction we only add to exactly one tree. So the only property that is here is maybe not so obvious is why it stays a weak chain. So this is what I want to show you. This will be the last part of the proof. So I want to show that Tm prime up to Ti prime is a weak chain. Okay, so let's see. So just to remind the definition, this means that if I take the vertices of any Tj prime here, it should intersect the cube defined by Tj plus 1 prime up to Tm prime. Okay, so this is just the definition of being a weak chain. Now this holds, first of all, this holds for, the only case we actually have to be careful is where j equals to I. So this sort of holds automatically if j is at least I plus 1, because we knew it held before. And all that we did really in this process is we took all these trees, Ti plus 1 to Tm prime, we shifted them by the same direction, and then maybe we added some edges. So we never removed the edges, right? So this property remained. So we only need to show it, so we just need to show it for j equal to I. Okay, so let's see. So in fact, to do this, I will actually shift them once more. So let's pick some, node Vi in this tree, I guess, Ti. What's that? And thank you, this is not equal to the empty set. So how are we going to do it? We're just going to pick Vi in Ti, okay, any node. And we're also going to shift them, so we're going to shift everything. So Ti plus 1 up to Tm and Ti plus 1 prime up to Tm in some direction, let's say j double prime inside this I prime, inside the directions where all of these are invariant, so that they agree with Vi, so that they agree with Vi on I prime. Okay, so we have Vi, this coordinate, Vi has some values. I can shift those by whatever I want in this direction. And since they remain sensitive, they also remain sensitive because they're subtrees. So everything remains the same. Everything's still legal. So now this should work. So now what we have? Vi is a member of Ti. Okay, let's see. What should I delete here? Okay, maybe I'll delete this part over there. So, actually, let me delete this one. So let's see, what do we have? So we're nearly done. So in fact, what we want to prove is this invariance, right? So let's actually remember that we don't really need to prove this. We just want to prove this invariance, right? So the Tj stayed inside Tj prime. It's still fine. The directions are disjoint, and this cube equals that cube. So this is the last thing we have to prove, right? So what do we know? So we want to prove. So the goal is to show now that the cube defined by Ti up to Tm equals the cube defined by Ti prime up to Tm prime. So these are bigger than that. So no, this direction is obvious. So what we want to show is the other direction, right? So I want to show this direction. So what do we know? Well, we know by induction that's a cube defined by Ti plus 1 prime up to Tm prime equal the cube defined by Ti plus 1 up to Tm. And this didn't change as we shifted them by the same direction, right? So all that we have to show really is that Ti prime is contained inside this cube. But it does. Why? Well, Ti prime contains Ti. So what we need, so we need to show that Ti prime is a subset of the cube defined by Ti up to the Tm. Okay, so let's see why.
Ti prime equals Ti.
What's that?
Ti prime equals Ti at this one.
Yes, and it equals. So this is in fact going to be Ti, and it's here. So we're done. So you see, this was like a bit messy. And if you could put this sensitivity tree conjecture, everything would be much more simpler. But this is what we know. Yeah, that's it. Thank you.